Hello everyone, welcome to Devjit Decodes. In today's video, we are going to talk about this assembly line scheduling. This is another very important algorithm and we'll be seeing how this particular thing is also applying the dynamic approach. But before that, let us understand what is the problem statement it is trying to solve. Suppose say you have some raw materials or a structure of a car and you want that car to be ready, right? So in that case, you went to a manufacturing company, right? And in that manufacturing company, there are several assembly lines. As you can see, this AL1 and AL2, I have taken two assembly lines for this example. Now, each of the assembly line does the same thing. That is, first it sets the engine, then it sets the wheel, then it paints the car, then goes for testing, and then finally the car is ready. If you can check, the assembly line 2 is doing the exact same thing, right? So what is our goal here, or what we are trying to do, or what kind of, as I have said that it will be coming to the dynamic part. So what kind of problem it should be? If you hear this, it should come in your mind that it should be an optimization problem. So either we are trying to minimize something or we are trying to maximize something. Here what we are trying to do, we are trying to make sure that our car will be ready in minimum amount of time. So this should be another minimization problem. Now if you can see, suppose say you have given the structure of the car here. Suppose say to move your structure of the car from here to say assembly line 1, you needed 5 unit of time, and to move from here to here you needed 7 unit of time. Now saying this, you suppose I have given to first place, you have given to set the engine here, right? Now whenever you have given to set the engine to the assembly line 1, to move from one particular station to another station inside the same line, it doesn't have any cost, it doesn't have any time. Okay, so this particular thing will not have any time. But suppose you have set the engine from assembly line 1, now you come to, or you want to come to the assembly line 2 for the wheel setting, because you have seen might be that wheel setting at assembly line 2 takes less time. But to transfer it from assembly line 1 to assembly line 2, it will take some time, say T1. So this particular cross edges, it will be having some value, again T3, T4, T5, this is a transfer time, right? But if you stay inside the same assembly line, then in that case, transferring from one station to another station will have no cost, right? So what is our goal? Our goal is to make sure that we will be giving structure of the car at the initial stage, and you will be seeing whether to move to AL1 or AL2, whether to stay in the same assembly line or to switch between the assembly lines, and at the end of the day you will be getting this car delivered at the minimum amount of time. As simple as that. That is what we will be trying to solve. This is the problem statement, right? Now if you go back to the problem statement, what have I written? Manufacturer is a manufacturing company, and inside that manufacturing company there are multiple assembly lines. Here I have taken two, and each line has several stations, and we need to make sure that the car is ready by the minimum amount of time. So again, this is a minimization problem, this is an optimization problem, so we'll be trying to see how we can do that. Now before going there, let us just understand that say, can we do it using the brute force manner? Can we do it using the brute force manner? Now if you see, suppose we want to do using brute force manner, what will brute force do? Brute force will check all possible combinations, or say all possible solution combinations. So in that case, if you want to apply brute force, as you can see, say for S11, we have only one choice, that is it is coming directly from here. S21, it has only one choice, it is coming directly from here. But if you see S22, so it can either come from this or it can come from this. That is, you have done the engine in this part, but then you have moved to this one. So S22 can be here straight away, that from the second assembly line you are coming here, or you can come from one, right? Any one of this thing, you can come from here as well. Same for S23, if you can see, it can directly come from S22 or it can come from S12, right? So for each of them, apart from the first one, for each of the, say there can be n number of things. So for each of them, that is for each of the station, there are two choices. There are two choices. So if there are n stations, how many choices are there? It is 2 to the power n. It is 2 to the power n. right? So it would be like 2 into 2 into 2 into up to n. So it should be 2 to the power n. So if you see, the time complexity becomes order of 2 to the power n. That is nothing but absolutely exponential time complexity. That's why brute force will not work. Now the question is, can we apply dynamic? Yes, we have understood that this is an optimization problem, this is a minimization problem, but as I have spoken in my dynamic video, that there should be two properties that needs to be satisfied to apply this dynamic programming concept. So what are those? First one is optimal substructure. What is the meaning of optimal substructure? The meaning of optimal substructure is that the bigger thing or the bigger solution depends on the smaller solution. That is, a bigger optimal solution depends on the smaller optimal substructure solution. So if you can see, to find out the time at S13, we are dependent on whether this one S22 or S12, whether it is coming directly to this or directly to this. It will depend on this one because we have previously calculated S12 and 22. So to calculate S13, we need the optimal result either at S12 or the optimal result at S22. So there is a optimal substructure, definitely, right? The next one is overlapping subproblems. So is there any overlapping subproblems? Let us see. Suppose say you want to calculate S13. Now to calculate S13, what are the things you need to calculate S13? Either it can come from S12 or it can come from S22. That is, it can come via this path or it can come via this path. So if it is coming via this path, it is coming directly from S12, and if it is coming via this path, it is coming from S22. So S3 is coming from S12 or S22, right? Now if you see, S12 is either coming from this path or this path, that is S11 or S21. So S12 is coming from S11 or S21. Next, S22. If you see S22, either it is coming via this path or it is changing this path. So S22 is coming via S21 or S11. So S22 is coming from S21 or S11. Now if you can see, there are repetitive subproblems, or they say there are overlapping subproblems. So we have both the things available, as well as it is an optimization problem. So we can surely apply the dynamic programming concept, right? Now whatever we have discussed so far, let us sum it up using this equation. So as you can see, this is written that f1 of j is nothing but minimum of f1 of j minus 1 plus a1 of j, or f2 of j minus 1 plus t2 of j minus 1 plus a1 of j. So what is this, all these things? It is really easy to understand. Let us see. See, it is written that a1 of j is equals to the time needed to process at station j of line 1. Okay, so what is this? Suppose you want to set the engine, but to set the engine you need some time, right? So let us see this diagram, or let us see this particular thing. So what is this? Suppose this is the engine setting part. So to set the engine you need 20 unit of time. So this is what it is saying, that a1 of j, this 1 stands for assembly line number and this j stands for station number. For an example, as S11 indicating that assembly line 1 and station 1, here it is indicating the same thing. So we can write it out. A1 of 1 is nothing but, from this equation it is 20. A1 of 1 is 20. Now if you see, if you want to write A1 of 2, that is this one. So this is 40. What is the meaning again? Time needed to process at station j of line 1. Similarly, I can do it for say A2 of 1 and A2 of 2 and so on. We can write it like this. Now what is T1 of j? T1 of j is nothing but the time to move from line 1 of j to line 2 of j plus 1. So if you see, this is the transfer time. So you are moving from line 1 of j, that is line 1 of this, to say line 2 of j plus 1. Because if it was j, it will be j plus 1. If it was station 1, it would be station 2 of another line. Because obviously it cannot be like this. It cannot remain inside the same station. It doesn't make any sense. It should be in the next station. So what should I write? T1 of, suppose here, T1 of 1 is this one, 15. T1 of 1 is 15. Similarly, T2 of 1 is equals to 20. This one, right? So if you can see, this is nothing but time to move from line 1 of j, that is line 1 of j, to line 2 of j plus 1. Line 2 of j plus 1. That is, if it was 1, it will be 1 plus 1, 2. Right? Next, what is f1 of j? Because this is what we are calculating. So how do we calculate f1 of j? First of all, what is f1 of j? Minimum time to reach station j of line 1. Minimum time to reach a particular station of a particular line. So what is f1 of j? Suppose you want to reach here. You want to reach here. First of all, to reach here, what is the total? To complete up to this part, what is the total time needed? This is the entry time, 5, and this is 20. That will be 25. Because first there is no choice. You have only one path. For this second one, it will be 10 plus 10. So this will be 20. This will be 20. Now, to reach here, you have two choices. Either you can come via this line or you can come via this line. So if you can go from the same assembly line, what will be it? 25 plus 40. So this is 65. 25 plus 40. Or you can come via this line. So if you go via this line, it will be 20 plus 20, 40 plus 40. So this is 80. 80 is nothing but 20 plus 20 plus 40. This 20 is this 20. This 20 is this 20. And this 40 is this one. So if you can check, we are choosing between 65 and 40. What is this 65? 65 is nothing but 25 plus 40. And 80 is nothing but 20 plus 20 plus 40. Now if you can check, f1 of j, that is what we are trying to calculate. f1 of 2. f1 of 2, right? That is fast assembly lines station number 2. f1 of 2 is equals to minimum of f1 of j minus 1. So if you can check, f1 of j minus 1 is what? This one, 25, because we have calculated 25 plus a1 of j. What is a1 of j? 40. Because it is a1 of 2, 40. Or f2 of j minus 1. That is what? That is, you are coming from this part. So what is the f2 of j minus 1? This is 20 plus t2 of j minus 1. What is t2 of j minus 1? Transfer time from the second particular assembly line. So this is this one, 20. So again 20 plus 20 plus a1 of j. What is a1 of j? This one, a1 of 2, 40. So you will be choosing minimum. So it is 65 and it is, I guess, 80. So you will be choosing between 65 and 80 and you will be choosing 65. That means it remains in the same assembly line. No need to change for this one. Right? So this is the meaning. So between this one and this one, it simply means it is coming from the another line, it is staying in the same line. So you will be choosing between these two. That's the equation I am saying again and again. That's the thing we are doing here again and again. Right? So you will be choosing here 65. So this one is chosen. So this is the meaning of f1 of j, minimum time to reach station j of line 1. Now we will be solving a complete problem to understand these things in a very, very vast manner. And then everything will be cleared out. Also, we will be talking about the complexity of this dynamic programming approach. So let's just see that. Okay, so now let's just solve this particular problem so that everything gets cleared out. As you can see, we will be having two tables. One is the cost table, another is the tracing table. This will be used to store all the cost to find out the minimum cost, and this would be used for the tracing the actual path. I will be coming one by one. Now if you can see this one, this is say assembly line 1, this is assembly line 1 and this is assembly line 2. Okay, so what is this one? This is nothing but the time required at station 1 of assembly 1, and similarly for all the things. And what is this is transfer time from station 1 of assembly line 1 to assembly lines 2's station 2. This is the transfer time, that is 2. And accordingly all the things are given. We have taken some raw material and we have manufactured a car. And these are the assembly line 1, assembly line 2, and these are the stations, as we have already talked about. Now if you can see, if we want to go from this to this at the very fast time, for the very fast time, so how much time will it take to complete all this thing? There is no choice here, only one choice. So it is 3 plus 10, 13. It is simply 3 plus 10, 13. And what is the time taken for this one? 5, that is the transfer time, or this is say entry time, entry of 1 and entry of 2. So entry time of this particular phase and accordingly the fast time, that is the A21 according to the equation. So what will be it? 5 plus 11, that is nothing but 16. So if you can check the first thing, that is for the first assembly line, it became for the first one, this is 1, This is 2, this is 3, this is 4, this is 5, and also on. So for the first one, it is 13 and it is 16. And what this trace table says, that from where this 13 is coming? This 13 is coming from 1. Because it is first time, there is no need to check, and this 16 will come from this second one. You can write simply like this, because it is obviously one direction, because there is no second choice. You cannot write anything. So for the first time, it is writing. For the next time, we will be understanding what is this trace table mean. Now, if you see the next one, if we want to come here from the same assembly line, and if we want to complete, so how much time? Up to this is 13, and as it is using the concept of optimal substructure, so it will be taking help of this one. So it will be 13 plus 12, that is 25. If you come via this same assembly line, if you stay in the same assembly line, up to this part it was 13, and to complete this one, 13 plus 12, that is 25. But you have another choice. It is not the single choice. You can come from this one as well. So you have completed the first part here. You have completed the first part here, and now you want to move back to here. You do not want to kind of, continue in this path. You can come from this path as well. Okay, you can come from this particular path as well. Now, if you can see, what is the thing we can do for this one? 16 plus 2, that is 18, plus 12, that is nothing but 30. That is nothing but 30. So, if you do this, what is the meaning of this one? That you have taken simply in the same assembly line. But what is the meaning of this one? That you have come from the another assembly line to this one. So it is 16 plus the transfer time is added, that is 2, that is 18 plus 12, that is 30. So which one should you choose? You should choose 25, because it is giving you the minimum time. So you should choose 25, because you have two options and you have chosen 25. And from where 25 is coming? From the first assembly line. So it is 1 again. Right? Now if you want to see this one, if you stay in the same assembly line, first let us come from 1, because let's fix this convention that the first value we will be writing is coming from 1, that is assembly line 1. It will be easy for you to recalculate. That's why I'm just saying. So if you come here from the first assembly line, so what is the time? 13 plus transfer cost is 2, 15 plus 8. So that is nothing but 23. Right? And if you would have stayed in the same line, it is 16 plus 8. That is nothing but 24. That is nothing but 24. This 23 is coming from the assembly line 1 and 24 is coming from this one. So which one that is staying in the same assembly line? So which one is minimum? 23. So we will be taking 23. And 23 is coming from which line? Line number 1. So we will be writing 1. Right? Now if you see this one. So before this stage, because again there is a concept of optimal substructure, so which one will be taking? 25. So 25 plus 6, it is now similar. You can calculate by yourself. 25 plus 6, that is 31. And if you come from this path, it is 23 plus 1, that is 24, plus 6, that is 30. That is simply 30. So what does it mean? Which is the minimum? This one is the minimum. Right? If you come via this path, if you change the line, this is 30. So it would be 30, and here we will be writing 2. Because if you can see, if you're fixing this dimension, you can see this line, and you can check or you can tell that which value should be set. Because if the line is on the second value, 2 will be setting here. That's why I'm fixing the convention. You can do it in your mind as well, right? Now if you, for this one, if you check 23 plus 9, but we will not do this one first. We will be coming from this line first to make sure that the convention is fixed, right? So we will be coming from here 25 plus 3, 28 plus 9. So that is 37. 9 plus 3, 12, 12 plus 25, that is 37. Now if you come via this line, it was 23 plus 9, that is 32. 23 plus 9, no transfer cost, same assembly line. So 23 plus 9, 32. Which one you are picking? Second one. So you are picking 32 and you are here in 2. Right? Now if you go 30 plus 7, 37. And if you go via this line, 32 plus 2, 34, 34 plus 7, that is 41. If you can check 32 plus 2, 34, 34 plus 7, 41. So which one are you taking? 37. So this is 37 and it is coming from 1. Similarly, if you check this one, 30 plus 1, 31 plus 7, 38, and from here it is 32 plus 7, 39. So which one are you taking? 38. So it is 38 and it is 1 because it is coming from the first one. Now if you check this one, 37 plus 11, that is 48. And if you come from this root, it is 38 plus 2, 40, 40 plus 11, that is 51. So which one are you picking? 48. So it should be 48, and here it is coming from the first one, that is staying in the same assembly line. Now if you check this one, if it is coming from the first one, it would be 37 plus 3, 40, 40 plus 8, that is 48. And if you stay in the same line, 38 plus 8, that is 46. So which one are you picking? This 46, 46, and it is coming in from the, that is staying in the same line, that is 2, right? Next, if you check this one, this is nothing but the exit time. This is exit time. This is EX1 suppose, and this is EX2. EX2. Now if you check this one, this will be 48 plus 2, that is 50, and it is going to say 1, obviously from the first only option is left, and here it will be 46 plus 1, that is 47, and here also it is coming from 2. Now which will be giving you the optimal result? The last particular column is giving you the optimal result, and it is saying that 47 is the minimum time required, because it is saying the completion is done, the card is delivered. 47 is the minimum time required to get your card delivered from this stage to this stage, right? So from where this 47 is coming, now we need to trace back the which path. If you see 47, if you come via this, it is coming from 2. That is simply it is saying that it is coming from this direction, because obviously we have taken this one, 41 plus 40, 46 plus 1, 47, right? So this is coming from this direction. Now move to this value in the previous column. So if you move to this value of the previous column, if you can check, it is also saying that it is coming from 2. It is coming from 2. That means what? That means this. Now if you move to the same particular value of the previous one, that is previous column, if you can check, it is coming from 1. It is coming from 1. That means what? It is saying that up to which you are going via this line, but here it was coming from 1. Here it was coming from 1. So now you are at here. Now this is a very tricky state. Now you are at here. So this particular thing is coming from what? Because you need to move, because up to this you are in the below line, but now you have moved to this part, so you need to move and need to check from where it is coming. It is coming from 2. So it is coming from 2, right? Now if you go here, you are here, so you need to come to this particular part, and from where it is coming? It is coming from 1. It is coming from 1, right? It is coming from 1. Now this particular one, you go to 1 and you see that it is coming from here. So if you see, the path is like 3 plus 10 plus 2 plus 8 plus 1 plus 6 plus 1 plus 7 plus 8 plus 1. If you can check, 13, 15, 23, 24, 30, 31, 38, 46, 47. 47. So this tracing is a little tricky. So let us just regroup it again. What we are saying, the last value has come from 2. The last value has come from 2. So you are saying simply that it has come from this direction. Now if you come to this particular value, what this is indicating? That go to this particular value and this stay in this particular assembly line. So it is staying in the same line. So it is staying in 2. Now this 2, this particular 2, it is also saying, what this is indicating, it is also saying that it is coming from the second assembly line, right? Now if you come to this particular thing, this value indicates that it is coming from the first assembly line. It is coming from the first assembly line. Now if you are at the top, you should be standing here. So you should see this value. You are not seeing this value, you are seeing this value. So this is saying that it is coming from this one. Similarly, all this thing. So this tracing is a little trickier. You need to understand it more and more clearly. But this particular value is indicating from where it is coming, and this particular thing also indicates that where to move. If you can draw this kind of lines, you will be understanding it in a more clarified way, right? So I hope this is the answer for this one, 47. And what is the complexity, by the way? What is the complexity of this one? Because whenever we were using the concept of brute force, it was order of 2 to the power n, absolutely exponential. But if you can see here what we are doing, if you have seen that particular formula we used before this, that is, we are going to each station one time. If there are n station, we are going traversing to each station one time, and each time we are doing what? We are doing some constant amount of work. So that is nothing but order of n for traversing and order of 1 for doing the constant amount of work. Because what we are doing, we are simply summing up something or something like that, simple mathematical operation. So it is nothing but order of n. So in this video, we have rigorously talked about what is assembly line scheduling, how the things are working, what is the formula behind it, why it is using dynamic programming concept, and how to solve a complete example of this thing, and why brute force is failing, and what is the complexity. So that's it about this video. Thank you for watching, and stay tuned for the next videos.